All right, I'm back. We are on page 328. We're on the first problem. We were talking about optimization, which is an application of derivatives, finding maximums, minimums. It's just like you put them in context. And so now instead of just finding x coordinate or whatever, it has a meaning, right? So let's see. Consider a rectangular industrial warehouse consisting of 3 separate spaces of equal size. So I focus on industrial as if that's like the meaningful thing. Rectangular warehouse, 3 separate spaces of equal size. So can we draw that? I feel like we can. So let's see. I'm gonna go like here, here, here. Okay, so it's rectangular. And then it has 3 separate spaces of equal size. So then I need to cut this like here and here. So those all have the same size, which means, what should we do? All right, I'm gonna call this x. So this will also be x, and this will also be x. And then I'll call this y. So this is y, this is y, and this is y. And then while we're doing it, x, x, and x. So I need a lot of material to make this. Okay, so assume the wall material costs $200 per linear foot, and the company allocates $2,400,000 for the project. Which dimensions maximize the total area of the warehouse? So there's like a lot of assumptions being made here. I'm going to assume all that money is going to go to buying the materials. I don't know. I mean, I feel like it's really the only way to deal with it. So it's $200 per foot, and we need a lot of feet. So it's going to be 200. So we're working on a helper equation here, right? So there's going to be x's and y's, but this is not the thing we're trying to optimize. This is just like given information. It's like in a video game or in a story when you like meet some like random character and they start giving you like all this information. You're just like, that's really interesting that you're telling me all these things, but like I don't need to know any of this, or so I think. And then suddenly the quest appears. And it turns out all that information was useful. All right, how many x's are there? There are 6 x's, and there are 4 y's. All right, and if I do that, that should cost me, I'm gonna assume I use every dollar that I have. 2, 4, 1, 2, 1, 2, 3. Okay, it should cost me that. So what can we do here? I'm gonna divide by 2 and knock off 2 zeros. So I'll get 6x plus 4y. So 1, 2, so 1, 2, 1. And then I can divide by 2 again, which I kind of feel like I should. 3x plus 2y equals 6,000. All right, that's sort of manageable. It's not great, but this is going to be my helper equation. So maybe I should highlight this in some weird color. So you are my helper equation. So that guy's going to come in, save the day when we have some formula that involves too many variables. Which dimensions maximize the total area? All right, what is the area of this thing? So the area of our little warehouse, actually it's an enormous warehouse. I don't even know if it's enormous or not. I mean, you think Amazon has some warehouses that are like out of this world big. You should look it up. They're like not big enough to have their own weather system. I think that one of like NASA's like launch facilities or whatever has like a building that is so big it has its own weather system, like it could potentially rain. I don't know. These are all good things to Google. Probably spend hours looking them up. All right, area of this place. 3x times y, I think is the area. Yeah, right, because each of them is x times y and there's 3 of them, or you could think like the big thing is 3x cross and then y. Either way, too many variables, right? We have an x and a y. We need to get rid of one of them. So we go to our helper. So interestingly, the helper equation has 3x in it, and our function has 3x in it. So I'm actually going to do this. I'm going to say from the helper equation that 3x is equal to 6,000 minus 2y. And then I'm going to take that. I'm going to take this and do a little substitution and get that the area is 6,000 minus 2y times y. All right, so our area is now just a function of y, which is not an issue, right? It could be a function of any variable because it's just going to be power rule because I'm going to distribute. So 6,000y minus 2y squared. Okay, so that's my area. Let's find, I'm going to switch colors here. Let's find a prime is going to be 6,000 minus 4y. It just occurred to me that Amazon Prime, there should be a math joke there somewhere. I don't know what it would be. It's like the rate of change of Amazon. I don't know. The rate at which Amazon's growing. Amazon Prime. All right. So then a prime equals 0 gives me y equals 6,000 divided by 4 is 1,500. That's large, right? Especially because x is going to be I don't know, 1,000, I guess. So let's see. So we need to prove that there's a maximum when y is equal to 1,500. I'm gonna use I guess I'll use the first derivative test. I could use the second derivative test. I could, and the lonely critical point theorem, because there's only one critical point. Actually, let me do that. So a double prime is -4, which is less than 0 for all y, right? So we can say that a of y, so let's see, a of y has a relative maximum at y equals 1,500 because a prime of 1,500 equals 0 and a double prime of 1,500 is less than 0. Okay, so that's relative maximum. Since y equals 1,500 is the only critical point, a of y has absolute max at y. Ooh, that's a bad at symbol. That's like multiple at y equals 1,500. Okay, so that's lonely critical point. You're going to use that a lot. And what's nice about it is the candidates test, you have to like find the area, and I don't think we didn't need to do that. We just needed the dimensions that maximized it. So it's always in your mind as soon as you don't need the actual like value of the function. So then the dimensions. So dimensions of the warehouse are, all right, so if I take 1,500 and I sub it in, where would I be? So if I sub it in here, then I'm going to get 6,000 minus 3,000 is 3,000, and then divided by 3 is 1,000. So the dimensions of the warehouse are actually 3, I'm going to say 3 by 1,000 by 1,500, right? So it's 3 1,000 by 1,500 units. So you could say 3,000 by 15. I don't really know. I think like this clearly communicates it if you like add in the picture. So I'm good with that. What is the area of each compartment in your solution above? So the area of each compartment is just x times y. Let me go back to black. Area of each compartment. You do a lot of writing. So is 1,000 by 1,500 equals 1,500 and then 3 zeros. 1, 2, 3. 3. Wow. Square feet. 1.5 million square feet each. That is enormous. Okay, so this is a good problem. I liked every part of it. Did I get it right? I think so. But let's go to the calculator and just like redo the problem, because this This is one of the things you run into is like a lot of the problems that you do now in calculus are basically algebra 2 problems that you could have done just by using a calculator, which is totally fine. So what did we have? We had the area was 3x times y. We had 200, 6x plus 4y. So this is what you should be doing. Like when you do a problem, you should then try to do it again on your calculator. Let's solve this for, so I did a weird thing. So I'm gonna solve this for x and get that. And then, I don't know, is that the same thing? Minus, whatever, we're gonna keep going. And so the area as a function of y was 3 times x and then times y, and I'm gonna such that this is true. So what's the area as a function of y? Okay, derivative of a of y. You should be using templates when you do this with respect to y. Solve the answer equals 0 for y. We get 1500. I then did the second derivative. So if you're typing, which you very well might be, because if you bought the calculator, it comes with a license for your computer. You probably threw it away. They don't make a big enough deal of that, that it's like there. A of y, comma y. Second derivative, do comma 2. And it's going to find the second derivative. You get this, -4, so less than 0 for everything. So that is, in fact, it. And then x is this, such that y equals 1500. We get 1000. So we got it. All right. So I'm going to go back to the notes and close out this page. And then, nope, not close out this page. We got one more problem on this page. So I'm going to be back in another video to do the second problem that's on this page. And I will see you there. So I hope you are finding these helpful. Whoa, where are we scrolling? All right. I hope you're finding these helpful. See you then.